So in this video, we're just going to briefly explain what eigenvalues and eigenvectors are. So here's the idea. If we have a square matrix, so if A is a square matrix, we want to find a scalar, lambda. And by scalar, remember, we just mean that lambda needs to be any real number we want. So we want a scalar lambda, and we call that scalar an eigenvalue of the matrix A if we can find a vector, a non-zero vector. This is important. If we can find a non-zero vector x such that when we multiply the matrix A times the vector x, we get the same result as if we just multiply the scalar times the vector x. So again, an eigenvector, if we have a square matrix A, an eigenvector is just a vector x such that A times x equals a scalar times x if we can find such a scalar. And so in the videos that come subsequently, our job is going to be to figure out first what the scalar is, and then once we have the scalar, figure out what the eigenvectors are. So again, this is kind of interesting in the sense that we are wanting to find a vector x such that multiplication by a matrix gives the same result as multiplication by a scalar. So that, it's kind of counterintuitive that you'd be able to do that. And so here's how we work out what we need to do to calculate eigenvalues and eigenvectors. So if we want A times a vector to equal a scalar times a vector, we could then introduce the identity matrix here. So if A is an n by n matrix, we can insert the identity matrix here. Remember, the identity multiplication by the identity matrix is kind of the real number analog of multiplying by 1. So by doing this, we preserve x. It doesn't change x when we take this product. And the reason for doing this is this gives us a matrix that's the same size as the matrix A. And we're going to want to do a subtraction, so this is going to make the subtraction possible. So then the next thing that you do is you subtract this piece from both sides like we did here. And once we've subtracted this from both sides, now the right hand side is going to be equal to the 0 vector. Not 0, but the 0 vector. And then we can use the distributive property to factor the vector x out. And this is why the introduction of the identity matrix here was important, is now I have two matrices of the same size occurring where the subtraction is, which means the subtraction is possible. So this is just a manipulation from, hey, I want to find x such that ax equals a scalar times x, and we're manipulating it into this final form. And what we want to recognize is this final form is actually a homogeneous system, like we saw in the previous set of videos in the previous homework. And we know that a homogeneous system always has the trivial solution. So if we let the vector x here be equal to the 0 vector, we would get 0 times this, the 0 vector times this stuff here would be equal to the 0 vector. So if we have a homogeneous system, we know that we always have the trivial solution. It always exists. And remember, in the previous set of videos, what we did is we said, hey, what do you need to do to ensure that you have non-trivial solutions? And so what we remember is that if the inverse of this matrix right here, because this is just a matrix, if you crunched it, you'd have a matrix times x equals 0. So what we needed was this matrix to not be invertible. So remember, we know that if we have bx equals c, if b has an inverse, then we can solve for x by doing b inverse times c. And then we're guaranteed that the solution is unique. And remember, we came up with the formula in the last set of homeworks that b inverse is equal to 1 over the determinant of b times the adjoint matrix for b. And so the way that you get the inverse to not exist is you let the determinant of, you want the determinant of b to be equal to 0, so that we get a division by 0 in this formula, and it causes this ratio to be undefined, which means b inverse doesn't exist. And if B inverse doesn't exist, we can't isolate X. And we're in a situation then, if the trivial solution exists, we know there must be infinitely many solutions. So this is just like a single matrix B right here. And so what we want to do is force the inverse of this to not exist by figuring out what are the values for lambda that will make the determinant 0, because then we're guaranteed to have infinitely many non-trivial solutions. And that's key because the eigenvectors need to be non-zero vectors. So the idea here is we know the trivial solution exists because this is a homogeneous system. How do we force non-trivial solutions to exist? Well, we find values of lambda that will make the determinant equal to 0 so that we can't calculate the inverse and multiply both sides by that inverse, generating a unique solution. So in the next two videos, we'll show an example of finding the eigenvalues and eigenvectors of a 2 by 2 matrix, and then we'll show an example using a 3 by 3 matrix.